You know, civil engineering is fundamentally all about predictability. We look at historical data, we crunch the numbers to find the absolute extremes, and then we build massive hulking structures designed to withstand very specific hydrostatic loads. But what happens when the baseline data we use to pour literally millions of tons of concrete simply expires? The Three Gorges Dam is, without a doubt, an absolute marvel of 20th century engineering. It was built to hold back the mighty Yangtze River. But right now, there's this massive conflict brewing between static 20th century engineering data and a rapidly shifting 21st century atmospheric reality.
Welcome to This Explainer. Today, we're putting on our hard hats and conducting a rigorous infrastructure risk assessment. We're going to dig right into the math, the atmospheric physics, and the operational limits of literally one of the largest structures on Earth. We want to see exactly how it holds up against a threat its original designers just couldn't fully predict. To do this systematically, we're going to break this down into 5 key areas. First, the original design basis. Then, the atmospheric physics shift, compound event threats, sedimentation, and finally, the eroding safety margin. All right, starting with number 1, the original design basis. To really wrap our heads around the risk here, we first have to understand how civil engineers actually calculate safety for these massive structures. And that brings us to a really critical concept, the probable maximum flood, or PMF. Think of this as the absolute mathematical ceiling of disaster. It represents the theoretical worst-case scenario. Now, the PMF for the Three Gorges Dam was calculated using rainfall records, river flow measurements, and atmospheric models that engineers had available to them back in the 1980s and 90s. For them, this was the ultimate, unbreakable hydrological baseline. So let's see what that design actually looks like during a real-world stress test. The dam's spillway was built to handle a staggering 116,000 cubic meters of water per second just to meet that PMF standard. During the intensely heavy floods of the 2020 monsoon, the peak inflow hit 75,000 cubic meters per second. That pushed the reservoir to 96% of its total capacity, but structurally, it was only operating at about 65% of the spillway's limit. This left a very comfortable 35% safety margin, which in engineering we call freeboard. That's the critical distance between the water level and the actual top of the dam. So the dam did exactly what it was designed to do. The 2020 event was extreme, sure, but it was perfectly within historical parameters. But here's where things get complicated. Let's move to section 2, the atmospheric physics shift. We need to look at the new hazard vectors that are rapidly tearing up the mathematical foundation of that original 1990s calculation. To understand exactly why the math is breaking down, we have to talk about the Clausius-Clapeyron relation. It's a fundamental rule in atmospheric physics, and it basically says that the atmosphere's capacity to hold water vapor increases by roughly 7% for every single degree Celsius of warming. Now, global temperatures have already risen roughly 1.2 degrees since pre-industrial times, and we're projected to hit 1.5 to 2 degrees by 2050. 7% might not sound like a huge deal on its own, but when you multiply that across the entire massive Yangtze River basin, it's literally the equivalent of adding several Amazon rivers directly to the sky. Bottom line, warmer air holds way more moisture, and more moisture produces far more intense rainfall. This perfectly illustrates the stark contrast between the era when the dam was designed and the reality we live in right now. Because of that physics rule we just talked about, by 2050, the atmosphere over the Yangtze Basin will be capable of holding 8 to 14% more moisture than it could when the dam's blueprints were first drawn up. And more water in the sky translates directly into a massive increase in peak discharge capacity, racing right toward that concrete. The real so what here is how this physics shift completely alters probability. A 2021 study published in Nature Climate Change showed that human-caused climate change has already bumped up the probability of a flood event, just like the one we saw in 2020, by 15 to 40%. And even more alarming from a pure risk assessment standpoint, events of that exact magnitude are projected to become 2 to 4 times more frequent by the year 2100. So, purely by the numbers, the extreme event that recently pushed the reservoir to 96% capacity, it's rapidly just becoming the everyday norm. Which brings us to section 3, the compound events threat. This is where we shift from looking at pure water volume to actual operational danger, because precipitation patterns are becoming dangerously spiky. You see, beyond just a single massive wave of water, climate change drastically increases the risk of multiple extreme rainfall episodes happening right on top of each other. Just look at the 2020 monsoon reality check. The Yangtze Basin got hit with 5 distinct flood peaks in just 6 weeks. Now, the standard operating procedure for any dam is to lower the reservoir between floods, right? You want to recover your flood control volume and restore that operational freeboard. But when storms hit back to back like that, the recovery window completely slams shut. Let's methodically walk through how this creates a cascading failure mechanism. Step 1, the first major flood peak arrives. Step 2, the reservoir fills up as it absorbs that initial shock. Step 3, because the climate is turning out this spikier weather with way fewer moderate breaks, the next extreme peak arrives before the operators have any time to safely empty the reservoir. And step 4, the dam's absorption capacity collapses. To prevent water from just overtopping the entire structure, operators are forced to release water downstream at massive rates. They basically have to sacrifice downstream protection to preserve the dam's structural integrity, which ironically causes the exact flooding the dam was built to prevent. All right, moving into Section 4, sedimentation accelerates capacity loss. Because the threats to the structure aren't just liquid, let's examine a secondary hazard vector that's physically reducing the dam's defensive capabilities right from the inside. Whenever we get these heavier climate-fueled rainfall events hitting the upstream catchment area, it causes absolutely massive erosion. This intense runoff washes huge amounts of sediment directly into the reservoir. And why does this matter for our risk assessment? Because solid mass takes up valuable space. In civil engineering, we talk about something called dead storage. That's the volume of a reservoir that can't be evacuated by gravity. Well, sedimentation is rapidly expanding this dead storage zone, directly stealing space from the critical live flood control storage that we desperately need. Just to put into perspective how aggressive this physical capacity theft can be, consider the number 97. That is the number of major landslides that occurred upstream in just 4 months back in 2010. As precipitation intensifies, the hillsides saturate much faster. This means we can fully expect the frequency and volume of these massive landslides to increase, practically dumping millions of tons of solid material right into the operational envelope of the dam. And that leads us to our final point, Section 5, the eroding safety margin. Let's tie this entire risk assessment together by evaluating the structure's expected 150-year design life against a worsening climate trajectory. The Three Gorges Dam was incredibly over-engineered to survive a 10,000-year flood. We're talking about an event with a 0.01% chance of happening in any given year. But watch how the statistical return periods degrade dynamically over the structure's lifespan. By 2050, global temperatures could easily be 2 to 4 degrees higher. Because of that, the mathematical certainty of the 1990s totally collapses. That 10,000-year return period? It's projected to become a 5,000-year flood by 2050 and a 1,000-year flood by 2100. What you really need to take away from this is a pretty profound realization about all infrastructure in the 21st century. The core threat here isn't that the concrete is going to suddenly crumble tomorrow. It's that the very definition of an extreme event is shifting right under our feet. The structure itself doesn't drastically deteriorate, but the environment it operates in becomes exponentially more hostile. And remember, this slow-motion thinning of the mathematical gap between safe and not safe doesn't just apply to megadams. It applies to the local bridges, the urban drainage systems, and the seawalls in your own cities right now. So here is my honest take as we wrap up this assessment. The dam survived 2020, and honestly, it will likely handle the 2030s and 40s just fine. But look at the long-term risk profile for the 2060s through the 2080s. You're dealing with a structure that will be 60 to 80 years old, carrying cumulative material fatigue and natural concrete degradation. Combine that aging structure with a 15 to 30% increase in monsoon intensity that is acting completely outside its original design basis. It is literally the ultimate gamble of operating a 20th century marvel in the middle of a 21st century climate. The dam was an incredible engineering answer to the past, but it's facing a future its designers simply couldn't quantify. So as an infrastructure analyst, I have to ask you, does climate change the equation? I'd absolutely love to hear your thoughts, so drop your own risk assessments down in the comments. And make sure you're subscribed to catch our next explainer, where we're going to analyze the cascading failure scenarios of what actually happens to electricity for 80 million homes when a mega dam stops working. See you then?